Welcome to This Explainer. Today, we're embarking on a masterclass journey straight into the fundamental hardware that powers basically everything in our lives, from massive desktop PCs to those tiny, smart light bulbs. Think of this as your ultimate foundational lesson in computer architecture. I am absolutely thrilled to be your guide today as we pop open the hood of the machines we rely on every single day. So before we start busting some major hardware myths, I want to pose a question to you. What is actually going on inside the central processing unit, or CPU? I mean, you know it as that little microchip that runs your apps, but how does it literally process all that information? Well, let's dive right in and completely demystify the incredible engineering happening right on your desk. Here is our lesson plan for today's explainer. We'll be looking at 1. Inside the CPU's brain. 2. The fetch, decode, execute cycle. 3. Myths of CPU performance. 4. Understanding instruction sets. And finally, 5. The world of embedded systems. Let's get to it. Section 1. Inside the CPU's brain. Let's start by laying down the foundation with the historical architecture that actually makes all of modern computing possible.
Believe it or not, we owe our modern computer structure to a brilliant 1940s concept called the von Neumann architecture. And what's really fascinating here is what this idea replaced. Picture this. Before the mid-1940s, early computers literally had to be fed data while they were running. You couldn't just store a program on them. They required constant manual human intervention. John von Neumann changed the game with the concept of the stored program computer. It introduced a CPU that accesses memory directly, storing both the programs and the data together, and then executing instructions in a logical sequential order. It was a total game changer.
Now, inside that CPU, we have these things called registers. Think of registers as the CPU's highly organized, extremely fast short-term memory. Consider this your study guide for the 5 special purpose registers that keep everything perfectly synchronized. First up, the program counter, or PC, stores the exact address of the next instruction. Then, the memory address register, or MAR, holds the memory location that's currently being read or written to. The memory data register, the MDR, holds the actual data coming in or going out. Next, we have the current instruction register, CIR, which stores the instruction that is currently being decoded. And finally, the accumulator, or ACC, is where the arithmetic and logic unit temporarily stores data while it's crunching calculations. So how do we connect all these registers, the memory, and the input-output devices? Well, the computer uses 3 system buses. You can think of them as parallel transmission highways where each wire carries exactly 1 bit of data. First, the address bus carries memory addresses, and it's a one-way street. It only travels from the CPU to memory. The data bus, however, is bidirectional, shuttling actual data and instructions back and forth. And the control bus, which is also bidirectional, carries critical timing signals from the control unit to ensure the entire system stays perfectly synchronized. Section 2. The fetch, decode, execute cycle. Now that we know the internal parts, let's step methodically through exactly how they process instructions. Let's see how all this builds into a functioning machine. Every single action your computer takes, literally every click, every keystroke, relies on this fundamental 3-step cycle. Step 1. Fetch. The CPU fetches the next instruction from memory. The program counter sends the address to the MAR, the data is fetched into the MDR, and then it's copied right over to the current instruction register. Crucially, the program counter then increments by 1, getting itself ready for the next round. Step 2 is decode, where the CPU interprets what that instruction actually means. And step 3 is execute, where the CPU passes those decoded instructions as control signals to the correct components to actually perform the action. Fetch, decode, execute, over and over, literally billions of times a second.
Section 3. Myths of CPU performance. Let's pivot for a minute, act as mythbusters, and uncover what actually makes a computer fast.
You might be thinking, hey, if I want a faster machine, I just need to crank up the clock speed, right? Well, the system clock does synchronize operations, producing, say, 3.5 billion cycles a second in a 3.5 gigahertz processor. But it's a massive misconception that you can just increase this endlessly for better performance. Pushing the clock speed past the BIOS design limits, which is a practice known as overclocking, will actually cause unsynchronized operations. Basically, instructions just won't have time to complete before the next one starts, and that leads to frequent crashes, severe instability, and serious overheating of the CPU. Here's another really common myth. Doubling your processor cores automatically doubles your processing speed. Sure, multi-core CPUs alleviate the need to constantly push clock speeds higher, but there's a catch, and the math behind it brilliantly illustrates why.
A dual-core processor communicates between its two cores using just one channel. Simple, right? But a quad-core requires 6 distinct communication channels between its 4 cores just to stay coordinated. That increased need for internal communication inherently bottlenecks the potential performance gains. So yes, it's a great improvement, but it is certainly not a simple one-to-one doubling of speed.
Section 4. Understanding instruction sets. Let's clarify how these hardware components actually understand the commands we want them to carry out.
So the real crucial point is how we actually speak to the CPU. Every single CPU uses what is called an instruction set. Because the CPU only has a limited set of electronic circuits physically built into it, there is a strict, limited number of operations it can understand. Each instruction is made up of an opcode, which tells the CPU what action to perform, like add or JMP, and an operand, which is the actual data or the memory register that needs to be acted upon. All software running on a computer, no matter how complex, eventually boils down to these simple, fundamental instructions.
Now listen up, because this is a major trap for students and a very common misconception. Do not confuse programming code with instruction sets. They are absolutely not the same thing. High-level programming code, the stuff written by developers, cannot be directly understood by the hardware. No way. It always needs a compiler or an interpreter to translate it down into the low-level instruction set that the specific CPU's electronic design actually understands.
Section 5. The world of embedded systems. Finally, let's step outside the abstract desktop PC and look at how this architecture is applied in the real world.
It's a huge misconception that all our smart devices are computers in the traditional sense. A true general-purpose computer is multifunctional. You can completely change its software to do entirely different tasks. Embedded systems, on the other hand, are a very specific combination of hardware and software designed to carry out a dedicated set of functions. They are highly specialized, often feedback-oriented systems, and they're usually built around a microcontroller, which basically has the CPU, RAM, and ROM all crammed onto a single embedded chip.
Just consider a modern vehicle. It is absolutely packed with embedded systems. It uses sensors to constantly monitor analog or digital inputs, things like oxygen levels or fuel pressure, and then it automatically outputs signals to manage fuel injection, anti-lock braking, and even exhaust emissions in real time. These are completely dedicated, closed-loop systems that operate instantly based on feedback, all without you having to manually calculate anything while you're cruising down the highway.
And this technology scales all the way down to incredible simplicity, too. Even an everyday object like a smart LED bulb relies on a microcontroller embedded system. That tiny chip allows it to receive Bluetooth signals, process time-of-day scheduling, and even adjust colors or dim the light in response to natural light sensors. All of that happens entirely in the background, without any human intervention.
Now, the design of these systems brings immense benefits. They are incredibly small, they're relatively low cost to mass produce, they sip very little power, and they offer extremely fast reaction times. But, putting my teacher hat back on for a second, I have to point out the significant drawbacks. Because they are so highly integrated, they are notoriously difficult to upgrade. If a non-programmable embedded system needs a simple software update, you often just have to throw the whole thing out and replace it. And troubleshooting them, that is a highly specialist task.
Which brings us to a really critical modern dilemma. I'm going to leave you with this final, provocative thought to ponder. As our everyday devices become increasingly smarter, but infinitely harder to upgrade and fix, are we trading our long-term environmental sustainability for short-term convenience? Are these brilliant embedded systems inadvertently accelerating a wasteful, throwaway society? Thank you so much for joining me in this masterclass explainer. I really hope this lesson has completely transformed how you view the devices surrounding you every single day.